I'm Henry Blanchette, yeah, and this is some work that I did with Niki and Leo about liquid proof tactic macros. They're not tactics, and I'll talk more about that now. So you've probably heard a little bit about Liquid Haskell by now, and you've heard that it's this framework built on top of Haskell that lets you write specifications and proofs about your Haskell programs. We've talked about how to do these proofs, but I'm going to step back a little bit and talk a little bit more about the structure of proving and how Liquid Haskell is working. So we can look at this little example here. We have a property that we've written called associamin, and the goal of this is to specify that this min function of two natural numbers is associative. So the way we wrote that is in these little annotations where we have the syntax for writing the Liquid Haskell specification, and we have a refinement on the end of type. It has type proof, which is just an alias for units, and then we have this refinement, which is a Boolean predicate. And you can see how n, the natural numbers, are defined, and this min function, I haven't given the definition, but it's the min that you expect. So the way that Liquid Haskell works is that first it's going to reflect this data and these functions into this intermediary representation in liquid fixed point. And then it's when you want to check your refinements are true, it's going to throw that to an SMT solver and expect that SMT solver to decide whether or not they hold. Additionally, there's this other layer on top that's been developed for helping proof automation called PLE, which is proof by logical evaluation, where the equalities that result from defining your functions can be also lifted into the SMT solver, and then they can be applied automatically to basically beta reduce your function applications, so you don't have to do it manually. So this isn't a difficult proof. Again, not starting off with anything too hard. But you can kind of think about, okay, how do we prove this? Well, we're going to do some sort of induction because we're working on the natural numbers, and we need to expand out the min case when the inputs are successors. So there's more efficient ways of writing this, but here's one way that you could write this proof. So we have the same setup we have before, but now we've expanded the body. So we're doing this nested pattern matching on the three arguments, A, B, and C. And in most of the cases, we get this trivial is sufficient to prove it. Trivial is just an alias for the unit value here. And it's trivial because if you get to that point, the SMT solver can actually just decide automatically that the refinement holds. There's only one case in which we actually needed to give it some information, which was in the final step here. Can you see my mouse? Yes. Which we needed to make a recursive call to associamin. And in terms of proofs, this corresponds to using our inductive hypothesis. So pretty straightforward. But this is kind of a big proof that you had to write out for something really simple, right? You're just inducting 3 times. So wouldn't it be nice if we could write this in a more simple way, like I just described? And that's exactly what liquid proof macros let you do. So we could write it just like this. You can see here I'm using a Template Haskell quasi-quotation here to provide our own syntax for writing these. So how would you read this? Well, you have the same function as it looks in normal Haskell, but the body is going to have these macro calls in sequence. You have 3 inducts, and then there's this auto macro at the end, which will do a simple sort of proof search to look for things in context that are going to be sufficient to prove your goal as long as you can find something. And I'll go into more details about I'll go into more specific details about how this is expanding in just a second here. But you can see how it corresponds exactly intuitively to what we just saw. But how exactly does it expand? Well, I can go through this step by step. So just replace our body with the sequence of macros that we want to expand. We have these 3 inducts. So the first induct, that's going to correspond to a pattern match on A. And it's going to copy the rest of the macro sequence into both of the branches that are resulting. If you've used calc tactics before, this should look familiar to how the semicolon combinator works. Similar thing's going to happen for inducting on B, and then finally inducting on C. So now we've expanded our sequence of macros into this large tree structure where all the leaves are these uses of auto. So what does auto do? I mentioned it does a simple sort of proof search. So it's going to look in your context both for sort of hints that you can use, and also in this case, since we're doing inductions, it added a socialman to the context as well as the things that you get from deconstructing the arguments that you're inducting on. So in this case, there's a couple ways that you could call use your inductive hypothesis. So it's going to expand that last auto on the final line to this big, this triple and is a proof combinator, something that you saw before that takes two different proofs and just adds their refinements together, essentially. So this is really a lot of things that we're using at the end here, and it's definitely not all necessary for proving our proposition. If you had these macros expanding, say, implicitly, and you never had to look at them, maybe that would be okay. But it does increase the time that Liquid Haskell has to take to check to see that this is true. So we might care a little bit about efficiency and want to narrow this down to just the things that we want. So in fact, we implemented a pruning procedure that prunes this down to just the part that is necessary for the proof. So what's going to happen in the rest of the autos? Well, the same thing, but those ones we know it's going to prune everything away and just result in trivial, as we'd expect. Okay, so that was a pretty simple example, but let's look at something a little more interesting. So here's another proposition that we'd like to prove, LM insert. So to describe it in English, we want to say that if we insert X into a list XS, then X is going to be an element of the result. Okay, straightforward enough. Well, how would we go about proving that? Well, I've written here a proof macro script that encapsulates, it looks like it changed the font a little bit, but you ignore that. Encapsulates the idea of how you would describe this proof in natural language, just straightforwardly. So you want to say, okay, I'm going to do induction on XS, and then this notation here is just for giving names to your arguments in a similar way to how Cox induction works tactic. And then we want to, only in the case where we have X prime in scope, we want to condition on whether or not X is equal to X prime. If X is equal to X prime, well, then that means that X is at the head of our list, so we're done. We know that it's an element. But if it's not equal to X prime, then we need to do some sort of induction because we know that X has to appear somewhere else in the tail. Okay, so how would this proof script expand? Well, we can do the same thing as before, replace our body with the script we need to expand. First, we're going to expand the induct in a similar way that you saw before. And now we're going to get these two cases. So I mentioned this briefly, but this syntax here is sort of a named guard. So it should only expand to the body of the guard when the name that you specify is in context. So in the first case with nil, X prime is not in context. So this should not do the condition. In fact, it can't because it's not well scoped if it does that. But we found also that it's useful to have these autos at the ends of your scripts, and it was so common that we decided to just make it implicit. So you can think of every script as ending with an implicit auto. So because of that, in this case, if we're going to ignore this condition macro, it's just going to replace that with auto as if it was at the end of the sequence. And then in the second branch here, we have X prime in context, so we can actually reduce that to the condition, and the condition is going to run, and it's going to give us this branching on the whether or not X is equal to X prime, and then the autos are the result. We do a similar sort of expansion as before, where it does a simple proof search in context to find the things that are necessary to prove the result, if it can prove the result. And we get these results. So trivial in the first two cases, and in the final case, we need to do induction, similarly to how I described it informally at the beginning. Okay, so now you've seen sort of me stepping through very manually how this is expanding, but let's take a look at how this tool is to actually use. So I have a video here. Let's see if it works. We have a little bit more interesting proof that we're trying to do here. We're trying to prove this proposition, height mirror. So this takes a tree of natural numbers and proves that the height of that tree is equal to the height of the mirror of that tree, where mirror takes a binary tree and switches around the order of the branches. So this first part, com max, is a lemma that we're going to have to use, and it's really simple to prove. You just do some inductions. That's all you need to write. So if we use the tool and we run it on com max, it's going to run for a second here as Liquid Haskell. First it expands, and then it checks to see that the result meets the refinement. So it expanded to this part here, and now it's checking to see if it can prune anything. And in fact, it is going to try to prune that last one and replace it with trivial, but it found that it couldn't do that prune, so it's done. It needs that com max recursive call at the end. Okay, so that was pretty straightforward. So what does this one look like? Well, the note here that you should take in the body of this script is that we're doing an induction on T, as you would expect. But then we're calling auto in a more interesting way here. So we're giving it our lemma, com max, that we thought we would need. And additionally, we are giving it height tree and mirror tree, which are the functions that appear in the refinement here. And the reason that you include them as these hints is because we might need to, say, run com max with an argument that has height tree applied to it. So there's sort of this nested structure where you're building up these things that you want in context, and you might need to nest them more with each other. So there's a implicit depth to auto, which is 3, which is similar to other tactic systems, and you can specify here as the last argument. So if we run this, it'll do a similar thing that we saw before, except it's going to be a much bigger result. Scrolls down a bit here. Oh wait, this is the same one. Go to the next video. Okay, here we go. Okay, so we run it on height mirror, and it's going to do a similar thing. And I'll mention this later, but there certainly is a bottleneck here where when you're doing the pruning, yeah, you can see it's quite a big search here. So I'm not going to make any claims about the efficiency of this for sure. Definitely future work. But one of the main reasons why it's slow is because every time it prunes, it needs to run Liquid Haskell again to check to see if that pruning was valid. And you might wonder, well, why does it need to interface with Liquid Haskell in such an indirect way? Well, I'll get to that. Okay. So we did a bunch of these examples with independently selected benchmark. This was a variety of proofs that are propositions that were written as quick check properties that were checked in a real world library for Haskell. This was part of Havidi's master's thesis. So we had a lot of these proofs, and it turns out that proof macros are really helpful for simplifying your proofs. You can often discharge a proof in 1 or 2 macros if they're simple proofs. And just to be specific, these were over inductive data structures like natural numbers, lists, binary trees, that kind of thing. And just to give you a brief summary of what that looks like, well, we were able to reduce the size of the proof you would have to write by hand by about 57%. So it's a significant reduction, but that's an average. So some proofs are really easy by hand anyway, but whenever you're doing a lot of this control flow analysis over the functions that you're proving about, you basically end up having to rewrite your entire function in your Liquid Haskell proof, and this can simplify that a lot. So I want to mention a few takeaways here from what you would expect, what you would like to have when you use this tool. So what I really intend this to do is to aid with conciseness and understandability. So when you're writing your proof, rather than making it look just like your Haskell function and essentially just writing another Haskell program, you can write it in a more understandable way that follows the control flow that you think about your program taking. So in the examples you saw, instead of having to do this complicated pattern match where you're going to call the recursive function on some arguments that you pattern matched on, you can just call induct because that's what induction is. In brief abstract, I would say the strategy that you take in doing this type of proof is that the logical proof by logical evaluation and SMT solver can handle the leaves of your expansion very easily because you don't have any more conditions to think about, any more data to destruct. That's exactly what SMT and proof by logical evaluation are good for. But it can't reason about all the different kinds of conditions and pattern matching that you could do. Otherwise, that would be way too way too many. It would be unreasonable to expect Liquid Haskell to do that automatically. So this gives you just the right amount of fine tuning so that you can do that efficiently, but also not have to write a super verbose proof. And if you're familiar with tactics, especially, you'll note that what's really nice about these kinds of systems is that small modifications in the implementation of the function that you're trying to prove a property about, or about the property itself, can often be proven the same way with the same script of proof macros. You don't need to actually change the macros because they will metaprogrammatically expand according to the definitions without that redundancy, writing the whole function again. And even similar proofs of different functions, they can be written in a same way as well. They can often just be a couple of inductions plus an auto, perhaps with a few lemmas included. So if you are interested in this, you would definitely like our paper. We go into a lot more details about certain options that are available in this system, especially around how auto works. Additionally, we have a couple other proof macros that I did not demonstrate, but are also very useful. And as I mentioned, we ran our evaluation on this large variety of examples. So if you're interested in using this system for yourself, you can go there and look through all the different kinds of ways that this macro system can be used. So to go into the details a little bit, the implementation is using Template Haskell, as you saw with the quasi-quotations. And this certainly comes with some upsides and downsides. So the upsides are that Template Haskell is a advanced metaprogramming system for Haskell and has a lot of support already. So we didn't have to build an entirely new system like was done, for example, in FStar. We can just take advantage of Haskell's already mature ecosystem. The library, the tool itself is built on a library that we wrote in Haskell. So if you wanted to, say, add more macros or modify how they work, you can extend the library and find it for yourself here on GitHub. So in the paper, you'll also find the full semantics for our proof macros. I'm not going to go into detail here, but you can find that formalization. So I thought this work was really cool, but it's certainly a limited prototype. So there's a lot of further work that I think would be really interesting to have. Like I mentioned briefly before, Template Haskell is a separate system, also built on top of Haskell, but it doesn't integrate very well with Liquid Haskell. So as you saw with the pruning, you have to run Liquid Haskell all over again once you do the expansion to see if you can remove anything. So it'd be nice if there was, for example, an API to Liquid Haskell so you could do incremental checking and modifications of your proof state. I think this also integrates well with interactivity. So this is something that Liquid Haskell is lacking, but would be super useful, is if you could step through your proof state manually and get information about what's changing, especially with related to how you're using the proof macros, in a similar way to how in Coq you can step through your sequence of tactics and see how your proof context is changing and your goal. Other than that, there's a few other more user-related things that would be nice. For example, deeper pattern matching. You saw the induction, and there's a destruct macro as well. They only support a very simple pattern matching technique. We also don't have user-defined macros. So I'm sure someone, I wouldn't be surprised if someone asked about this in the questions, but why do we call these macros exactly? I'm definitely willing to negotiate about what to call it. I'm not married to that name. But one of the things that our system lacks is having a sort of meta macro where you can define a new macro that's like a sequence of other macros. Our proof search that Auto uses is fairly simple. It's not doing anything fancy, and there's been a lot of work on this kind of stuff. But one of the main limitations is that the proof macro framework only interprets the non-refinement information about your program. So it doesn't actually read the Liquid Haskell refinement annotations. But if there was closer integration with Liquid Haskell, or if perhaps you wrote a custom parser over the annotations, then you could do some more advanced proof search where you actually take into account the refinements and perhaps what appears in there. And then as one final note, polymorphism. So the system doesn't currently support polymorphism. And the main reason for that is that since it's so you would need to have some sort of unification ability to check to see if the things you're generating with auto are well typed with polymorphism. And as far as I could tell, Template Haskell does not support sort of interface to using the type checker to unify type variables, for example. All right, and that's a brief overview of my project, and I'm ready to take any questions. Thank you for listening.